Hello everyone, this is the Unit 8 review by topic. We're going to start with topic number 1, exponential functions. Does this table model a linear or exponential function? So when you're looking for linear, remember you're looking for something that has a slope that is a constant rate. Exponential, not so much. All right, so this is all multiplication. So linear would be adding and subtracting, and exponential would be multiplication. So you could just basically say, okay, from 4 to 8, you would either add 4 or multiply 2. Well, the next one goes from 8 to 16, and that is multiply 2. 16 to 32 is multiply 2. So this represents an exponential function. And the way you could tell is that every y is increasing by multiplication. Every y is being multiplied by 2 and to get to that next y. And there you have it. Every y value is being multiplied by 2 to get to the next y value. What is the equation that models this data? Well, an exponential function is y equals a times b to the x power. So we have y equals, and a, we're going to put over here, a equals 4. That is the initial value. And the b is the multiplier, that is times 2. So we have 4 as the a, the initial value, times 2 to the x power. And that is the equation that models this data, an exponential equation. Identify if the following is linear or exponential. Again, linear is basically a steady and constant slope, a constant change. Exponential is not a constant. So a pool is being filled at a rate of 10 gallons per minute. 10 gallons per minute. The next 1 minute is 10 gallons. The next minute is 10 gallons. This is linear. A plant grows 10 inches every week. Again, a constant rate. So this was constant, and this was constant. So that is linear. So taking the highlighter out, the amount of YouTube follows doubles every month. Doubles is not constant. Not a constant rate. So that is exponential. When it doubles at different amounts every single time. Say like if you double 5, it's 10. Then if you double 10, that's 20. So it's not the same rate. That's how you know it's exponential. A computer application generates a sequence of musical notes using the function, and I'm going to highlight that function, where the number of the note in the sequence, where n is the number of the notes in the sequence, and f of n is the note frequency in hertz. Which function will generate the same note as function f of n? So the only way to really do this is in the calculator. Graph. I'm not going to say graph, but this is the best way to put it, is input in your calculator. So the first thing we are going to do is input this as y1 and then try the first one and see if which function here will generate the same note sequence as the f of n. So very easy. You grab your calculator, you're going to press y equals, and we're going to put 6 times 16, and then to the nth power, which is x power. So I don't care what that looks like. I'm just going to try the first one right now as y2. 12 times 2, and then to the 4x power. And I'm going to graph it. That is the first graph, and that is the second graph. It looks a little off right here. You see the difference between that and that right here. That's the difference, and you know that that is not the answer. Different numbers and everything if you go to the table, and you cannot pick that as your answer because it's not exactly the same. So I'm canceling it out. Then I go down to y2 and clear it, and I'm going to put 6 times 2 in parentheses to the 4n power. So put 4x power. So we're going to graph it and see if this one works out. So it almost looks like it is, but it might be off just a little bit. I just need to go to the table. 696, no. The numbers are exactly the same. Exactly the same. So you could tell if I go down and I see when it goes into scientific notation, everything's exactly the same. So I don't have to search anymore. 2 is my answer. All right, you put that in y1 and you put this in y2, and everything's the same. And I'll have to try the others. So in the savings account, number 4 is opened initially with $100. So initially with 100, the money in the account doubles. There we go with the doubles. Each year. Draw a graph that represents this situation. Does this situation represent linear or exponential? If it doubles, that is an exponential function. It's not constant. Key word here. Doubles, triples, quadruples. Describe a situation that would make this function linear. If they opened the account with $100 and then added $10 every week, that would be linear. It's a constant adding of $10. And there it is. If they open the account initially with $100 and added 25 each week, that would be a constant rate, and that would make the function linear. So I'm just going to graph and sketch a graph if that represents opening with $100 and the money in the account doubles each year. So these would be the years right here, and this would be the money. So I'm starting out with 100, and I'm just going to go and double each year. So it kind of looks like this and like that. You notice that this is not linear. It is a curve, which means that the slope is not remaining the same. What would the graph look like if the account lost double each year? If they lost double the amount, it would decline. And it would decline or decrease. And that's instead of going up like that, it would decline and decrease. All right, so the domain. Always graph in the calculator. Just put the calculator and up and go ahead and clear out your y1 and y2. And here is your domain, right? So the domain, you're just going to put this directly into the calculator, and you're going to press 3 to the x power. And we're going to see what that graph is. So that's the graph. If you take a look at that graph, and if you're looking for the domain, obviously everything to the left is negative infinity. Everything to the right is positive infinity on the x-axis. That means it's going from all the way to the left and up all the way to the right. So that is the domain. So all real numbers. If you're going to put this into a inequality, it is x is greater than negative infinity and x is less than infinity. Right? Interval notation would be parenthesis because you cannot be equal to infinity, and so the negative infinity would go there, comma, and the positive infinity would go there, end parenthesis. That is the interval notation for the domain. For the domain of the y equals 3 of x. And that says x, but it's good. It's all right. All right, this is f of x. It should say f of x here too. All right, so f of x. F of x equals 5 radical x. We're going to put that up. I'm going to move this over and clear that out. Y equals, clear that out. And we're going to put 5 second function radical x, square root of x. And we're going to graph it. And we'll look at that graph. So just take a look at the graph. It starts here and goes up forever. So first, we're going to see what the x value, what's the leftmost portion of x. It gets close to 0, but it doesn't seem like it touches 0. So I said like it doesn't touch 0. Do you see like the graph is right here and it looks like it almost might touch 0? If you go to the second function table, it does actually touch 0. So that means 0 is a part of this domain. So we're just going to talk about x. And remember, domain is the list of all of the x values. And x is greater than or equal to 0. That's what the domain is. Interval notation would be, since it's equal to 0, since 0 is included, it is a bracket instead of a parenthesis. And then just remember, if it goes on forever in positive infinity, if you're just going to take a look at the graph again, and you're going to say, okay, yeah, this goes to the right forever, that is positive infinity with a parenthesis because you can't be equal to infinity. Which equation is represented by the graph below? So this is nice and easy. All you have to do is just graph these and pick the one that it's equal to, the one that looks like that. All right, so I'm just going to pick up the graph right here and the graphing calculator and put y equals down. And the first one I'm going to do is nice and easy, 5 to the x power. So that right there does not look like this. So I could cancel that out. Grab the calculator again, press y equals, clear that out. You have 0.5 to the x power. Let's see if that one works. That looks like this. So we are going to circle it. See, if you take a look at it, that really does look like what that graph is. And we're going to just accept that as the graph that's right on here. If you really wanted to check, it looks like negative 2, 1, 2, 3, 4. Negative 2, 4 is a part of this graph. So I'm going to just check it. Negative 2, 4 is a part of the graph. Yeah, I'm just checking one. You could check another one right here. This is 1, 2, 3. Negative 3, 1, 2, 3, 4, 5, 6, 7, 8. This is negative 3, 8. And let's see if that one is on there. Negative 3, 8. Yes, that's the graph. 2 is your answer. For topic number 2, we have exponential growth. And exponential growth, very, very easy. Just remember, it is y equals, and it's a times 1 plus r, and you could either put x or t. All right, x is the time, t, time. Actually, I'm just going to change it to time because that's what it is. All right, so the first thing that we always do in class is to identify the initial value. So invested $4,000, that's the initial value. The 5% interest compounded annually, that's very important. And then the time, 6 years. So we have A is 4,000. The R is 5%, but you have to change that R to a decimal. It's 0.05. You move that decimal over 2 places to the left, and you get that 0.05. And then the T that they want you to identify what this investment grows to is 6 years. So I'm just going to go ahead and put y equals 4,000 times 1 plus 0.05, 6 to the 6th power. So what this looks like, and you don't have to put this point, you don't have to write this down, 1.05. A lot of times they ask you, what is the percent increase that is happening here inside parentheses? It's 5%. But again, you're just going to put this into the calculator. I'm going to clear it, and then we're just going to move this over to right there. And we are going to put 4,000, that was the initial investment, times 1 plus 0.05, or you could put 0.105, doesn't matter, to the 6th power. You press enter, you get 5,360.38. 5,360.38. And that is the investment after 6 years. So that makes sense because it started out as a $4,000 investment, and then it's going up to $5,360. If they wanted you to state the amount of interest that was made, how much money you made, it would be $5,360 minus $4,000, and you would get your answer. Sarah was given $500 when she was born. Let me highlight some important information. Her parents invested the money at a 5% interest rate and compounded annually. No deposits or withdrawals were made. Write a function that can be used to determine how much money Sarah will have in her account. Just remember, this is a growth, a 5% interest rate compounded annually. So this is A times 1 plus R, and then to the T power. So we're just going to put this in as A is 500. The R is 0.05, and the T is going to stay T, because all they want you to do is to create an equation based on the information given for any amount of time. So A equals 500. 1 plus R is 0.05, and T is going to stay T. So then when you write down that information and that equation, we're going to use it to figure out how much more she will have in her account at 25 years old than 15 years old. So let's talk about what's going on here, because I'm going to move this over. And this is when she was 15. So I'm going to put a 15 here. And then this is going to be 25. I'm going to use the same equation. Y equals 500. 1 plus 0.05, same thing. And then this is 25. So how much more money will she have in her account? So I'm just going to take this first one and move my face over. Move my face over some more. Move the calculator over some more. Clear it out. I'm going to have 500. 1 plus 0.05, and then to the 15th power, because that's at 15 years old. So at 15 years old, we're going to have y equals, and we're going to have a money amount. The $500 has grown to $1,039.46. $1,039.46. And then we're going to just go 500. We're going to do the 25 when she's 25. And put the 25 in for T. And we're going to get 1,000. So Y equals, for 25 years, 1,693.18. So we have these two answers here, but that is not the full answer, because they were looking for how much more money will she have in her account at 25 years. So we're going to put 1,693.18 minus the 1,039.46. And that's what we'll do in the calculator when we bring it up. We're going to just have 1,693.18 minus 1,039.46. And then we have 653.72. She will have in her account 653.72. And that's that. It's a lot of work for a question. Number 3, Jill invests $500 in a savings bond. $400 in a savings bond. The value in hundreds of dollars after X years is illustrated in this table below in hundreds of dollars, which equation will illustrate the approximate value of a bond in hundreds of dollars over time in years. So the time is X. So we're just going to basically look at these and see exactly what's going on here. See, maybe we could cancel out something. So first off, I'm just going to look. Okay, if this is in hundreds of dollars, first off, it's growing. All right, it's increasing. So I know that it is not a decay. It's a growth. So anything with a decay, and first off, this is 1.3235. That is not a decay. So that's out right there. This is a decay, but that's out because this is growing. So you can't say something is a decay and have it growing. So we have a couple of things that we could do. We could take this second number, 5.4, and divide it by 4. So let's see what that is. 5.4 divided by 4. And let's see what the common ratio is. The common ratio is 1.35. So what's happening right here is that it's multiplying 1.35. 1.35. It's growing. So this says this, and it's not. This is a decay. It doesn't even match. Doesn't match this. So that's out. This one is a 135. You could see what that is right there, and it grows. So that is your answer. If you put this directly into the calculator, just let me see, let me just show you what's going on here. If you could put 4 times 1.35 to the x power into the calculator and you graph it, it graphs like that. But if you press second function table, if you take a look at this table here given, 0 is 4, 1 is 5.4, 2 is 7.29, and 3 is 9.84. See how the tables match? If you put it into the calculator, y1, it will match the table. It'll match the table given. All right. Take a look at number 4. Mike knows, and I'm just going to highlight this right here, that these are points of an exponential function, and he wants to find another point in that function. First, he subtracts 6.5, 17.55. First, he subtracts that. Next, he adds this to that, and then he gets this point. And is he correct? So explain your reasoning. So all of this right here, and then I looked at it again, and this is an exponential function. So the fact that he is adding and subtracting to get the next number, 28.6 and 5, that is not, that's 28.6. That is not going to work for an exponential function. So we're going to explain the reasoning. He is incorrect because he's adding and subtracting to get to the next y. And you don't do that for an exponential function. Okay, so you see that I have his method was incorrect because he's adding and subtracting to get to the next y value. This was an exponential function. If this was an exponential function, multiplication would have to be involved. So the world population in 2000 was approximately 6.08 billion. The annual rate of increase was 1.26%. Find the growth factor. So we're just going to go ahead and take that percent and move it 2 places to make it 0.0126. So that is the growth factor. So just remember, you're putting 1 plus the 0.0126 as far as that goes, and this right here would equal 1.0126. Suppose the rate of increase continues to be 1.26. Write a function model for the world. Write a function to model the world population. So this is y equals, and then so the A is 6.08 billion. What we're talking about, the rate, the R, was this amount. This R right here is 0.0126. So we're just going to put that in as the initial value is first, which is the A, and then this is 1 plus 0.0126 to the x power or t power. All right, and that is that. Let x be the number of years past the year 2000. Define the world population in 2010. Well, first off, A is still 6.08. R is still 0.0126. And the T now is 10. That's because 2010 minus 2000 equals 10. And that's about it. So now we're just going to put that in. Y equals 6.08 times 1 plus 0.0126 to the 10th power. And we're going to grab the calculator and we're going to put that directly in. We're going to have 6.08. I'm going to clear this out. Graph, clear. 6.08. And put it in directly into the calculator just the way you see it. It's 0.0126. Close the parenthesis to the 10th power. And you get 6.89. So this is y equals 6.89 billion people. And that's it. So, number 6, a payday loan company makes loans between 100 and 1,000 available to customers. Every 14 days, customers are charged 30% interest rate. Oof. In 2013, Remy took out a $300 payday loan. Which expression can be used to calculate the amount she would owe in dollars after 1 year if she did not make any payments? So this is a growth, and I just put down A equals 300 because that's the amount Remy took out. The rate is 30%, so it would be 0.30. So we're just looking at Y equals 300, which all of them start with 300, so we're good there. It is 1 plus the 0.30, and then let's just kind of worry about the t in a second. So it's 1.30. So this is out, and so is this. So it's 1.30, 1.30, and we're talking about every 14 days right here, every 14 days. So we're just going to have to put 365 divided by 14. And that's exactly what number 2 says. It's not 14 divided by 365. You have to see how many times there were that she's going to be charged the 30% interest rate in that 365 days because she's taking it out for 1 year. And that is the answer. Not easy. Topic number 3, exponential decay. Remember, decay is y equals a. It's 1 minus r to the t. So the height of the f of x, bouncing ball, after the x bounce is represented by this, how many times higher is the third bounce than the fifth bounce? So I honestly, you could substitute in and figure this out, or you could just go ahead and, you know, just put it into the calculator, but we'll kind of, you know, just figure it out by hand first, and then I'll just tell you what the calculator is. So if time is 3, we're just going to put 50 is 0.5 to the third power. That's the third bounce. So this is third. This is the fifth. So this is f of 5 equals 50 times 0.5 to the fifth. So when you put this into the calculator, you're going to get 50. Let's clear it out, and I'll just tell you what is going on here. This is 0.5, and that's the third bounce. The third bounce is 6.25, so f of 3 equals 6.25. And then we're going to go over here and put the same thing in, but instead of the time being 3, which is the third bounce, we're just going to do the fifth bounce. And you get 1.5625. Then you're going to take you're going to see how many times larger, how many times higher. So you're going to divide your two answers. So this is 6.25 divided by 1.5625. When you put that into the calculator, you get 6.25 divided by 1.5625. And it's 4, exactly. 4 times higher. Again, you could put this into the calculator, and I'm just going to go ahead and see if that kind of works out. And we're just going to go to the calculator here. So the third bounce is 6.25. The fifth bounce is 1.5625. Then you divide it. So that's, you could do it by hand, or you could really just put it into, input into the calculator. So I'm just going to put or input and in the calculator. And look at the list. At the table of values. All right. So if a new car is purchased for $25,000, each year it depreciates. There we go. Write a function model that models the value of the car, then solve for the value of the car at the end of the 5th year. So let's go ahead and write down our key. A equals 25,000. The R equals 0.03 as a decimal, and the time will equal the 5th year. So we have Y equals 25,000, and then 1 minus 0.03 to the T. So now we're just going to go figure it out. 25,000, 1 minus 0.03, and then we're going to put 5 in. We're going to grab the calculator. We're going to clear the graph out and clear all those numbers out there. 25,000 times 1 minus 0.03, and then to the 5th power. Let's see what that brings you. This one will bring Y equals, instead of 25,000, it'll be 21,468. And let me just go 468, 35 and 35 cents. after 10 years, after 5 years, sorry. And there you go. For number 3, the function, let me just highlight it. I like highlighting. There we go. Models there, and y is millions of dollars. And at months X, how much money was earned in month 4? So let's go ahead, round to the nearest hundredth. So this is each month. So we're just going to talk about each month, and we're just going to put that into the formula. We're going to use that, 56.25. Nothing really, they're giving it to you. 0.78. So this is a 22% decrease, right? So 1 minus 0.22 is 0.78 to the 4th power. So if you put that into the calculator, you will get 20.82 million. So we're going to have 56.25. And that is 0.78 to the 4th power. And there we go. There's $20.82 million. All right. How much money was earned in month 7? A lot going on here. So you're just going to use the same equation. 56.25 times 0.78. Instead of 4, it's 7. Grab your calculator. Do the same thing. 56.25 0.78 to the 7th power. Y equals 9.88 million. Whee! I wish I had that. All right, so round to nearest hundredth. So I did for both of those. How much money was earned? How much more money was earned in month 4 than in month 7? So you subtract. That's nice. Subtract. So you have 20.82 minus 9.88, and you get $10.94 million. And that's it. Alrighty, so here we go. We have number 4 here with the amount of seconds. Let's go ahead and see what is going on here. Okay, so here we go. This table shows the radioactivity level, amount of seconds recorded in the time period, what type of function best models the data below. So first off, I noticed that the numbers are decreasing. So if the numbers are decreasing, we're talking about a decay. So first, all of my choices, this is a negative rate of a linear function. Positive rate, no, it's not a positive rate. And this is not a positive, this is not a growth. So those two are out. Negative linear or exponential decay. So we're talking about minusing 10. And then if you minus 10 again, that would be 0. It's not minusing 10. So that means it's multiplication of a half. So if you do 20 divided by 10, that I'm sorry, not 20 divided by 10. 10 divided by 20, the second number, divided by the first, you would get 0.5. And that's what times 0.5 times 0.5 times 0.5 and then times 0.5. So this is an exponential decay, not linear. How do you know? It's a decay because it is decreasing. And I just put that there. Decay because the numbers are decreasing. Exponential because the decrease happens through multiplication. All right, so number 5, materials A and B decay over time. They're telling you that it is a decay. And so this right here is 1, and material this is right here, which T represents D's, time in days. And which day will the amounts be equal? Calculator. So grab that calculator. And we are going to press Y1. We're going to get that out of there. So Y1 is 1,000. 0.5 to the 2t, 2x. And then we're going to put the other one into Y2. We're going to put 1,000, 0.25. .25 to the what power? T power, which is x. So we're going to graph him, and that graph right there, and that graph looks exactly the same. So we're going to just see exactly that all of the days represent the same, that they are the same. So which day will the amounts of material be equal? Every day. All values are equal every day. So number 6, population of bacteria modeled by this. I love when they give it to you right there, where T represents time decay, blah, blah, blah. Remaining bacteria time. What is the rate of decay? Very important question here. Popular question. So this is 0.98, right? So decay, remember, 1 minus what number equals 0.98. So it's 1 minus 0.98. So I'm going to grab my calculator and I'm going to go to graph and clear that. And then so this is 1 minus 0.98. We're going to get the amount that was 0.02. 0.02. All right, you see what that is right here. That is the amount of decay. We're going to move that 0.02 over 2 places, and we're going to get 2%. And the amount of decay is 2%, so that is your answer. So number 7, on the accompanying grid, sketch the graphs of, and I'm going to move my face over here so I can bring my calculator over here. Not over there. I'm just going to move it over here. And I'm going to put 0.25x, right, to the x power. And I'm going to graph that one first. So we're going to put graph down, and we're going to press second function and graph. And we're going to just look, because you actually can't graph anything that is beyond -1, 4. So this is -1, 1, 2, 3, 4, right there. 0, 1, right here. 1.25, right here. And I'm just going to go like that, ever so close. Just like that. And that's my graph. Right? So I'm going to just gradually curve it, just like this part. See what I'm saying right there? So I'm going to go ahead and see if I can do that with blue and the best that I possibly can on this pad. That is not good. That's the best I can do with that. All right, and so I'm just going to put this down here because I have to solve for y. You have to solve for y to be able to graph it. So we're just going to add the 2 on both sides. So we're just going to have to cancel that out, and this is 5y equals 10x plus 5. Then you divide by 5 on both sides. This cancels, y equals, this is 10x divided by 5, that's 2x, and then 5 divided by 5 is 1. So we're just going to graph that y equals in y2, 2x plus 1, and we're going to graph it. And just let's make sure this is 2x plus 1. We have it goes through once right there, and so we're just going to go ahead and graph that. Look at the table of values, or you could just do it by freehand. I'm going to graph this one. This is the y-intercept, and this is the slope, rise of 2, run of 1. So I'm just going to go ahead and not look at my calculator and just graph those points. At this point, you are going to grab your ruler, put arrows on the ends of each of the lines. So this is y equals 2x plus 1. It does cross right here. Right here. So that is 0, 1. So the solution is one solution. And it is 0, 1. And again, you could check that out. You can check it out. Zero, 1. You check it out on the calculator right there. Crosses at 0, 1. And if you look at the table 0, 1, 0, 1. That's the only point that it intersects. All right, to last topic. Consider the following patterns. Which pattern is geometric? So you just take negative 12 divided by 16, and you are going to get 0.75. And I'm just going to take 9 divided by negative 12 to just check this out. It is 0.75. So this is geometric, and which pattern is geometric? It is 1. For the next one, this is plus 3. That's a plus 3. This is a plus 5. This is a plus 7. That is linear. That's not linear, but it's not geometric. Right? So that's out. And then plus 12, plus 12, plus 12. That's not geometric either. This one is being multiplied, but it's a different multiple. So if you did 2 over 3 divided by 1/2, you have 2 over 3 divided by 1/2. You would get 1 1/3, which is 4 over 3. And then if you did 3 over 4 divided by 2 over 3, you get 1.125. So this is not geometric because it doesn't remain the same throughout. Which situation can be modeled by a geometric sequence? Just remember, geometric sequence is not something that is a constant. It is being multiplied. So you're looking for keywords. Cell phone company charges $30 for a month for 2 gigabytes and $12.50 for each additional. This is linear. That's a constant. Stays the same. 79 degrees in the car. Lower temperature, you lower the temperature of your air conditioning 2 degrees every 3 minutes. Linear. That's constant. Every 3 minutes that happens. Same amount. David's parents have set a limit. 50 minutes per week. He may play online. However, they will increase his time by 5% per week. There you go. Keyword. Percentage, in this case, means geometric. $1,000, $100, and $15 each week is linear. That's a constant. 3 is your answer. What is the common ratio, the R? Whoa, what's that? The common ratio of a geometric sequence whose first term is 5 and third term is 245. So 5 is the first term. The second term is, so this is a sub 1. This is a sub 2. A sub 3 is 245. So let's try times 7. 7 times 35. 7 times 5 is 35. So that's times 7. And then let's try times 7 again. And that's 245. 7 is your answer. It can't be the rest of them. 5 times 49 is too large. And so are the rest of them. So you could just kind of cancel those out. Right? And here we go with number 4. Number 4. You're looking for the common ratio of this sequence. So everything's common ratio. Common ratio. So we're going to divide. Let's just divide. Or find the multiple. All right. So how does it get from x to 2x squared? So you could just do 2x squared divided by x. That is going to give you 2 over 1. That is 2. And x squared divided by x is x. That's it. Right? So x times 2x equals 2x squared. 2x squared times 2x equals 4x to the third. See how it goes right here? This is times 2x squared. 2x, sorry. Times 2x. And then times 2x. Times 2x. So that's the common ratio. Number, well, that goes from 4 to 6, and there are 2 6s, so 1 is 5. So this is number 5. But it's really number 6. All right, so first 4 terms in this sequence, a sub 1 equals 40, and then a sub n, 3 over 4, a sub n minus 1 are, you just go ahead and you can do this. All right, so all we're just going to do right here is substitute. A sub 1 is 40. So we're going to go to a sub 2. I'm going to cancel this out right here. And let's see what's going on. A sub 2 equals 3 over 4 times a sub n minus 1. It's 2 minus 1, which is a sub 1. A sub 1 is 40. Hopefully that didn't confuse you. A sub 2 equals 30. Then you go to a sub 3. A sub 3 equals 3 over 4. This is the previous term right there, the previous term. So the previous term is 30. Then a sub 3 is 22.5. So you know it's this right here. So this works out, 2 is your answer. This cancels, this cancels, this cancels, and that's it. So if you did a sub 4, it would be 3 over 4 times 22.5, and that would equal 16 7/8. And that would be your answer right there. All right, but you don't need to do that anymore. Number 6, because you have your answer. Number 6, what is the 8th term of a geometric sequence where a sub 4 is 216, r equals 3? I would not use the formula for this. I would just wouldn't. Sometimes it's easy to use the formula, sometimes it's not. But if you're starting with a sub 4, just remember the geometric sequence formula is given to you on the reference sheet. So this is the formula. But you need a sub 1 to use the formula. And I don't want to use the formula to work back to a sub 1. Can I? Yes. But do I want to? No. A sub 4 is 216. A sub 5, I don't know what that is. A sub 6, yeah. A sub 7, okay. A sub 8, that's what we need. So if the r is 3, this is the common ratio. If that's the common ratio, we are just going to multiply to get there. So 216, let me just bring this calculator up and see that 216 times 3 is 648. And then you could do times 3 again to get to 1,944. And then times 3 again to get to 5,832. And then times 3 again to get to 17,496. So just remember, you're just multiplying by 3 because they gave you the common ratio. And so a sub 8, the 8th term is 17,496. And that's it. We are finished with this review sheet, and hopefully that did help you. Thank you for watching. See you next time.